All right, hello physics students. Thank you so much for taking the time to watch this. Really what this is designed to do is to help you with the practice test, more specifically to really kind of help you with a lot of these multiple choice. So hopefully you have this practice test. Really a lot of what we'll be going over is ways to interpret these motion graphs if these are confusing you. So that's really my focus here in this next little bit of the movie is the multiple choice piece and kind of understanding the motion graphs. If you don't have a copy of that practice test, please let me know. Also be aware that the practice test is on our website. So hopefully you've kind of been peeking at that answers. In fact, what I think is worthwhile is maybe even have that practice test with you as you're listening, or even have the answer guide up in another window as you're listening and watching. That all should be worth your time and very valuable. Okay, going over the multiple choice. Let's just start with question one. Let's just look at a position time graph. And really the question was, if you make a position versus time, so remember the title is always y versus x. So we got our position in centimeters, our time on our x-axis in seconds. I don't know, let's just kind of make up some data. And really what this data set is similar to, this is our car in the hall. All right, this is our first day of school. I don't know if you remember the title of that lab, our first day of school, was constant velocity. So this motion graph, this position versus time graph, should match kind of similar results of what we got in school that first day. I don't know if you remember, it was, this is I guess similar. We were kind of taking every 3 seconds and marking where it was. A lot of our cars would make it, I don't know, about 30 centimeters or so after 3 seconds. If we were to try to mark it every 2 seconds, it'd probably get to about 20 seconds or 20 centimeters. It'd be difficult if we tried to mark where it was every second. A lot of us would get it kind of close to that 10 centimeter mark. After 4 seconds, I think you can kind of see this pattern. It would get to be about 40 seconds or so. So really, yeah, then we could, and this was like one of the few hand-drawn graphs that we did, but just kind of keeping track of where it was with respect to time, we could get our marks, we could get this line. I'm hoping you recognize that that line means constant velocity. And in fact, our definition of velocity is based on this graph, where if you create that line, your slope is your change in y, your change in the y, divided by our change in x, and remember that is our definition of velocity. An example like this, so what did I have it at? Actually, we marked it about, so what do we have it here? This is quite simple. It went 10 centimeters in 1 second, so you could keep track of it that way. That works. So 10 centimeters in 1 second is the same thing as really 0.1 meters in 1 second. So you could write, so really you could write that as 0.1 meters per second. So that is about as easy of a constant velocity problem as we can give you. So once again, just kind of helping you guys remember our algebra here. But slope, a lot of times you could say, is change in y over change in x. I personally, my favorite way to think of slope, and really it's rise over run. A lot of times as these graphs get trickier and trickier here as we go, a lot of times just counting on the graph is very, very worthwhile. But change in y over change in x is the same thing as y2 minus y1 divided by x2 minus x1. Okay, so yes. Now let's take a look. Another way we could create a position versus time graph was our second day of school. And a good way to think of that is I had you guys rolling marbles down a ramp. If you remember, our ramps are those long tracks. They're about the same length as our table. So they start at 0, and this would be in centimeters for this one. But yeah, so our tracks were a couple meters long. That's the same thing as a couple hundred centimeters. So if I were to scale this axis here, we'll use these examples in the motion graph section as well. But if you kind of remember, on our position versus time for the marble, I had you marking it every second. So on our position versus time graph, once again our y versus x, our times here, we marked it every second. And that was tricky to do, but you only had the length of the table to try to cover in that 6 seconds. But depending on your incline, a lot of times after 1 second, that thing may have only gone about 10 centimeters. After 2 seconds, it maybe got up to like close to 20 centimeters or so, but not, it's kind of slow, slow. After 3, maybe it goes a little farther, maybe up to like 35 centimeters. After 4 seconds, it gets a quarter of the way down that ramp, up to close to 50 centimeters. Really, at like 5 seconds, it was about halfway. But by this time, it had been picking up a lot of speed, rolling a lot faster. So just in that next interval, that last second, remember a lot of people were kind of jumping across the table trying to reach that last mark. And that would be kind of close to the end of the ramp, close to that 200 centimeter section. So if we try to draw our best fit, it's not a line. This time we would draw a curve through there. And it's really that this curve, the thing I wanted you to remember from that, and remember trying to get those marks down, is that that curve really does indicate that the velocity is increasing. Or maybe a more generic way to say that is a curve on a position time graph indicates that there is a changing velocity. So that's what this curve shows us. And then if you kind of think of some of the computer graphing exercises we've tried to do, a lot of what it does is you get this curve and then it starts to kind of snap fit or draw these tangent lines at each point. Now if you draw these tangent lines, what I want you kind of thinking of is these tangents. So it's the slope of these tangents, and I like to play the pencil game where I just kind of hold it on the curve and look at how does a line touch it but not cross it. If you look at that slope of your tangent line, it's a position versus time graph. That's the same thing we've kind of been doing. That is our change in position. The slope of that is our change in y over change in x, our change in position over change in time. And on a curve where we're using these tangents that are changing, where our velocity is changing, really what we say is that slope at that moment, that's what we call the instantaneous velocity, or the velocity at that moment, the velocity at that instant. So instantaneous velocity is the slope of a tangent line, but still, once again, it's position versus time, and we get velocity from that. Okay. All right, so moving on. Now the next question, the next multiple choice question, so really these are just still questions, just getting you to look at these multiple choice and kind of think about all the aspects of those graphs. So number 2 here, we have set up a velocity versus time graph. So I think what is so important on all of these is to remember what that data is and remember what it's really measuring. So we've kind of tried to do a few activities where we're dropping tennis balls, dropping golf balls. If something is in free fall here, so let's look at our tennis ball. If it starts to fall, we could try to kind of mark where it is as it falls. In much the same way as we could have the tennis ball kind of fall past our motion sensor, I kind of had you guys dropping. Sorry, I had to check. Did that turn it off? No, I didn't. Okay, sorry. If you had that tennis ball falling past a motion sensor, it could pick it up. We dropped those kind of picket fence looking things past a motion sensor. But part of the idea with that is when you dropped it past a motion sensor, it could pick up its velocity. It could pick up its velocity and it was moving at that initial time. So our time here is in seconds. So as soon as it started picking up those positions at time 0, it may have already been moving. All right, and then it's going to move faster. Let's say after 1 second, maybe it gets up to a speed of like say 14. The next second it's moving past that sensor. Say it gets up to a speed of 24. And really I'm writing these down. Sorry, this would be free fall. So I'm writing these down in meters per second. After 3 seconds, it could get up to a speed of 34. After 4 seconds, it could get up here to a speed of close to 44. After 5 seconds, and really something to be falling 5 seconds, that is a long, long drop. So this is kind of exaggerated. Really, it's like climbing up to some of our taller buildings here in town to drop things and have that motion pick up the whole time. So it would be difficult to keep the motion sensor aimed at it, but if we did, this is kind of what we would see dropping it off a very tall building. And once again, like we like to do, our velocity versus time graphs are going to be lines. So here we can see our velocity increasing over time. Please, please, please remember our definition of slope. So the slope here is our change in velocity divided by our change in time. That is our definition of acceleration. So if this really is a tennis ball falling off one of the taller buildings in town, if it is this tennis ball in free fall, if I wanted to put numbers to this, and once again, I like rise over run. So my change in I'm going from 4 up to 54. So there's my change in y. So I'm going up 50. I'm going across from 0 to 5. So there's my change in x. But if you think about what that is, that's my change in y, meters per second, divided by my change in x. So that is our acceleration due to gravity, comes out to be about 10. So once again, the slope of a velocity versus time line is our acceleration. Okay, thank you. All right, a little bit more with this. So number 3 here on that. So once again, I'm just moving through this practice test, so hopefully you kind of still have this. Number 3 is also a velocity versus time, but in this scenario, we are curious about the area. So on my y, I got velocity. On my x, I have time. So So that's my y, that's my x. Once again, my time is in seconds. My velocity is meters per second. So let's say we had, this is that same picture. So I'm going to just, it's the same picture here, but I'm just going to kind of include 4 and 54 and keep those same increments of time set up there. So we go from 4 up to 54, and we'll finish off at 5 seconds, and this is 0. Okay, so and then we had our line on there that kind of looked like that. To find what the area would show us, and this is maybe a little tricky one to kind of look at, but if I wanted to figure out this area, and it's this area here underneath this line, if I can find this area, in fact that area does tell us, or does represent how far it's going to go. So that is a shortcut on our velocity versus time graphs. Using that area feature is a really good shortcut and very useful for us. So the way I'm going to find area is I'm actually going to break up this first piece. I'm going to kind of break it up like that. And I am going to look at this triangle here. So this triangle right here goes across 5 and it goes up 50. So that area is 1/2 times my base of 5. It goes up 50. So that's how far that little piece represents. But please keep in mind what you're looking at. There's this little extra bit down here that still I did not include. So that area of that piece, that little rectangle there, this piece only goes up 4. It still goes across 5. And it's a rectangle, so it's just base times height. And that would be 5 times 4. That, in fact, would be 20. And so how far did this thing fall? Like I said, this really is some of our taller buildings in town. No, this is a few hundred feet, more than that. So yes, just add those two together to get that total distance, that total. So yeah, that area is a good shortcut for us to try to find that. Now, a lot of people like, that's still once again, same question. So I'm going to keep that same graph where it really kind of, it's a velocity graph, it's time. These velocities are measured in meters per second. Our velocity went from 4 to 54. Our time went from 0 to 5. So same graph, and we just found that area. So if you remember when we did this, our previous answer, what did we get here? I think we got an area of, what did we say, 145 there. Okay, so that area piece was 145 meters. We can use equations too. And so a big thing a lot of you kind of learned on your own, but I want to kind of formally show you, is that using our equations, and so people say, well, if you want to know how far it goes, use this. Use our distance formula. We use this a lot. So if the distance formula tells you how far it goes, we kind of know, we're expecting this to be our answer here. It was free fall, so we've already kind of established that the slope on a velocity versus time graph, the slope is our change in velocity divided by our change in time, which we said was the acceleration. Now once again, if it's something in free fall, if you kind of think back to a couple minutes earlier, we established that that slope, that velocity changed by 10 meters per second every second. So that is our value for A. So if I come over here to the distance formula, the value of A that I'm going to substitute in is 10. Okay, the time, I can get that right off the graph. Now be careful here, this one is a free fall one, but from the moment we started recording data, please recognize it's right there is where we started recording data. That's time 0. So our initial velocity, it was moving. It moved for 5 seconds. So when I plug and chug here, 25, that's 125, 4 times 5, it's 20, but yay! Our distance formula works, our area feature works. Okay. So yeah, that is velocity versus time graphs. In fact, what I want to do is let's look at a kind of really complicated one. And if you think back to that launcher quiz we kind of did in class, and most of you guys did very well on that launcher quiz, afterwards I had you kind of looking at this page in the practice test. So we used Logger Pro, and so we were given this data set. But what I want to call your attention to is we started at 0. Let's look at this point right here. So this position goes about 1.5 meters, and we've kind of used our tangent feature to get all of these instantaneous velocities. So what you're looking at there is we just kind of said, yeah, I'll just kind of real quickly give you that same data set. But the point I wanted to look at was that 1.5 meters there. So once again, this is kind of, if you want to flip to question 39, it's a good way to think of how a data table, a data set, measuring and marking where things are with respect to time, allows us to use these equations and kind of show all these same relationships on a graph. So what you were doing is you were going through generating the graph, you used that tangent feature, it snap fit into place and gave you these very exact values for the instantaneous velocity of that. If I was to take this set of data, now once again I'm kind of ignoring this for a minute, and I'm going to set up a velocity versus time graph. So I'm going to make this my y up at the top. I'll make that my y kind of near the bottom. Once again, all these decimals a lot of times get confusing, but I'll make this my x and this my y. So my x, I'm just going to go up to about a second. I could put those points. I know it's a line, get lines on our VT graph. Okay. Now, that area trick again. So I'm just going to kind of estimate it. But really, if I wanted to find the area here, the area, so I'm just going to estimate this area. But that area should be how far it goes. So one thing to kind of look at here, let's do it kind of the same way we did before, where I'm going to I'll draw a triangle here and figure out that area. So that triangle, once again, 1/2 base times height. Just kind of estimating it. That base, well, that base runs all the way across, so that's really 1.1. The height, you know, it's close to 2.5, maybe just under, maybe, so I don't know. I'm going to call it 2.2. So I'm just kind of estimating that height, estimating that base. But yeah, what does that equal? That equals about 1.2 meters for that piece. The piece down below, we could kind of play that same game real quick here. So this little piece, finding the area of that rectangle. Area of the rectangle is base times height. Once again, that base is about 1.1 moving across. That height, I'm just kind of, I don't know, just guesstimating. It's about 0.3. So you estimate that. That's about 1 times 0.3. It's about 0.3. But if you look at this, so I get this 0.3 for an area, 1.2 for an area. If I combine those, so if I take the area of the triangle, the area of that piece, what do I get? Well, I get about 1.5. Just adding this, I add them together, I get right about 1.5. Now, remember, but the question was, how far does it go? Well, you already know how far it goes. You already know what its position is. You already knew that. But it's just kind of once again illustrating how all of these relationships fit together, and they all are just a function of marking where things are with respect to time. Okay, so question 4 on that practice test. So moving right along. It's what are vectors? Vectors become we've been using them a little bit. You guys have been drawing arrows. That's really all a vector is. But what that means is in that measurement, in that calculation, the direction really matters. The direction is significant. Right now, we've kind of introduced the idea that displacement or change in position, things could go forwards or backwards. A lot of times we'll say it goes positive direction, negative direction. But any measurement or any value that depends upon displacement is also a vector. So velocity depends on our change in position. Now, if velocity is a vector, then acceleration, which depends on our change in velocity, is also a vector. So these are 3 examples, 1, 2, 3 examples of vectors that I expect you to know. All right, so what have we tried to kind of illustrate, and what we're going to look at here in a moment is all of these motion graphs. A position versus time graph. Hopefully it's easy for you to see that, yes, you can find the slope on that. You can do your change in y over change in x. If you find the slope, that tells you your velocity. All right, if we create a velocity versus time graph and find the slope, well, that provides the values of our acceleration. So we can make a sketch of how the acceleration, or what the acceleration is with respect to time. Now, then working backwards, as we've kind of tried to illustrate, if I take a velocity time graph and find the area underneath that line, that gives me my change in position. That area tells me where it is, how far it's gone, what its displacement has been. The same thing could be true with an acceleration versus time graph. You can find the area underneath that, and that will tell you how the velocity has been changing. When you take calculus, you'll call slopes, or finding slopes, or finding that relationship of the slopes, you will call that finding the derivative. Instead of doing squares and triangles and rectangles and finding areas, you will still find the area, but instead of saying find the area, you will say find the integral, or integrate this function. Okay, so it's kind of a review of some vocabulary, but this, just marking where things were with respect to time, is the basis for physics, but it's really the basis for calculus and a lot of math classes as well. All right, let's take a look at 7. So we're dropping our tennis balls, or golf ball, or whatever it is. We've tried to say that the velocity will change by about 10 meters per second every second. So really, what is that? That's just saying so velocity is increasing. That means velocity changes. So please, please, in free fall, don't think it's like our first day of school. Don't think it's like our cars moving at a constant velocity. Free fall velocity is changing. To describe that change in velocity, that's acceleration. In free fall, that acceleration is due to gravity. And what do we see objects doing? Tennis balls, golf balls, marbles. They tend to accelerate at about 10 meters per second every second. Okay. Now then the other key thing is that acceleration due to gravity remains constant so long as we're here on Earth. Now what this class becomes is we do look at motion out in space. We do start to talk about how can we get satellites and rockets and things out into space and the challenge of that, and how gravity starts to change, or that acceleration due to gravity changes when you get out there. But here on Earth, here in our classroom, here at our bleachers, here for our problems in Chapter 1, that acceleration due to gravity remains constant. Now pretty soon we will start taking into account things like the wind pushing up or the air, and the force of those, but we're not quite there yet. But we'll look at how that affects motion. But certainly a piece of paper falling is going to be a lot different than our tennis ball falling. Okay. All right, let's take a look. So number 8, I like this one because it gets us thinking about how direction really matters. And what I mean by that is, how did you set up your tape measure? How did you kind of roll it out? And where did you mark your 0 spot? And which way did you decide to start measuring from? It's really always up to us to make those measurements. In other words, it's up to us to define what's positive and what's negative. And like I said, that happens immediately when you start measuring those positions. Now, if you look at this picture for number 8, we'll do a lot of detail on this one coming up. But quite simply, if you look at the picture, it says on there, and this is the thing, it has the way the ball is moving it's not relevant. It has nothing to do with the question. It really is there to trick you. But if we're saying it moves up the ramp, and up the ramp is negative. If you look at that picture on this one, on number 8, that thing moving up the ramp, moving up, going to the left, it says it's negative. So if up is negative, then that means coming down must be positive. Gravity, here in the room, here on Earth, here outside at our bleachers, gravity is pulling us down. So that acceleration due to gravity is down. So what must it be? That acceleration due to gravity must in fact be positive. Now, like I said, we're going to come back and do more of that at the end here as we kind of look at all of these motion graphs. So we'll come back to that. All right, another thing kind of think about, you actually, question 8, I was hoping you would think about our launcher labs. All right, so we did a few times, we were launching marbles all over the place, a couple days. We jumped up and down for a little bit. But very, very simply, and the whole thing, and I think just walking around, I know people got this. But obviously when you jumped, or when you took a picture of your marble, it stopped. And so that whole key is picking out that peak position. And that's really where we started to solve all of our problems from. What you guys have actually been doing when you plug and chug and solve our hang time problems, our vertical leap problems, our marble launcher problems, you've been solving these. You've been using that acceleration due to gravity. You've been plugging in a positive value. All right, if you are plugging in a positive value, for acceleration due to gravity, that means coming down is your positive direction. If coming down is your positive direction, that means going up is your negative direction. So it's really kind of another way to look at that picture in number 8. Okay, motion graphs. I think what I'm going to do, I am going to finish this, but it'll probably be a separate link. So we're going to look at position time graphs, velocity time graphs, and acceleration time graphs, and kind of help you try to make sense of all of those. Anyway, thanks for your listening here. Click on the next link here. Thanks.